Hello, and welcome to lesson 13 of this introduction to calculus with Wolfram U. The topic for this lesson is rates of change in the sciences. So let's begin with a brief overview of the lesson. So let's say you have a particle which moves along a straight line, for example, and the position at time t is given by this function s of t. That's t cubed plus 2t minus 2. Now, once you have the position as a function of time, what you can do is to compute the derivative, and then that will give you the velocity of the particle at time t. So here's the velocity, that's 3t squared plus 2. And once you have both s and v, you can then work out their values at any time. So for example, at t equal to 10, the values are 1018 and 302. And having done that, you can also plot the position velocity as a function of time over a certain period of time, in this case from 0 to 20. So in this very simple example, you see that the derivative gives you a nice way of approaching a problem in mechanics. And what we'll do is, in this lesson, to explore the applications of differential calculus in the sciences in various different ways. So let's again take up an example in mechanics where you have the position being given as a function of time, like over here. So you could work out the velocity, of course, as the first derivative, but you could also work out the acceleration, which is the second derivative. And once you've done that, you could ask questions. So for example, you could ask, when is the particle at rest? Well, it's at rest when the velocity is 0. So you could solve that equation and find out that the particle is at rest when t is either 2/3 or 2. And then you can plot the position, the velocity, and the acceleration and get their graphs. And you see that the position is given by the blue graph over here. The velocity is the graph over there, and it clearly intersects the time axis at around 2/3 and 2. And the acceleration is a linear function of time. So the derivative is a very powerful way of studying problems in mechanics. So let's go on another example where, let's say, you want to talk about the linear density of a rod. Now, if you have a rod and it, let's say, has got mass m and a certain length, then the average linear density is simply the mass divided by the length. But of course, what could happen is that the mass of the rod depends upon how far down you are at. So let's say the mass might be the cube root of the length, and in that case, you can talk about the linear density at a given length L. And that is given by the derivative of the mass with respect to L. So in this case, it's 1/3 times L to the power 2/3. And then, of course, you can work out the linear density at any given length. So in this case, if the length is 10, then the answer is about 0.07. And then you can plot both the mass and the linear density. And you see that the mass will, of course, continue to increase, but the linear density will go down as the length increases because of this expression for the derivative. Okay, so let's go on now to current. And if you have, let's say, a wire and some current flows through it, then the average current is the charge that flows in a certain period of time. But of course, the charge itself might depend upon the time t, like over here. And then the current at any given instant will be the derivative of that charge with respect to t. So at, let's say, at 1 second, the current is 4 amperes. And then what you can do is to plot the charge and the current and get back a plot for both these quantities. So let's go on now to chemistry. Now in chemistry, one talks about reactions, chemical reactions. So what happens there is that one or more reactants would undergo some process, and give you some products. So for example, you might have two reactants A and B that give you a product C. So one talks about the concentration of any of these in moles per liter, and then that concentration is of course a function of time. As time goes by, for example, A and B might decrease in quantity and C might go up in quantity. So in that case, the rate of reaction at an instant is given by the derivative of the concentration with respect to T. So for example, suppose that the concentration of C is given by 3T over 3T plus 1, then the rate of reaction at any given time is a derivative, so it's 3 over 1 plus 3 to the whole square. And then what you can do is to plot both these quantities, and you see that as time goes by, the concentration will increase, but of course the rate of reaction will go down as the system approaches a steady state. Okay, so let's go on now to biology. So in biology, one talks about population models. So for example, the population at time t might be given by 2t cubed plus t. And in that case, the growth rate for that population is the derivative of that population with respect to t. So in this case, it's just 6t squared plus 1. And then of course, you can plot both the population and the growth rate like I've done over here. Now, in practice, one might have a slightly different model. So for example, if you talk about the growth of bacteria, then it might happen that the population doubles every minute, for example, in which case you might get a formula like the initial population times 2 to the power t, and that's what is called an exponential function. Okay, so finally, let's go on to economics. So in economics, one talks about the cost function. So let's say a company might talk about its cost function, which is the total cost of producing X units. So here's the cost function in a particular case. Now, if you find the derivative of the cost function, then that's what is called the marginal cost. So the marginal cost, roughly speaking, is the amount of money it costs to produce an extra unit. So for example, we might ask, what is the marginal cost and the actual cost of producing the 1001th unit? So that's going to be the derivative of the cost at that value. Or you could actually find it by subtracting off the cost in both the cases. So 1001 minus 1000. And you see that they are very close, but not quite the same. So the marginal cost gives you a very good estimate of the cost to produce an extra unit. So once again, you can plot everything over here, the cost and the marginal cost, to get those two plots. Okay, so that brings me to the end of this lesson. And the main point is that derivatives are used universally in the sciences. So if you're a physicist, you might use them to study motion. And if you're a chemist, you might use them to study reaction rates. But if you're a biologist, you might use them to study growth rates. And finally, it's not just the natural sciences, but also social sciences. So in economics, you might use derivatives to find the marginal cost. And of course, there are many more uses of derivatives that we haven't spoken about in this lesson, but you will learn them as time goes by. But the key point is that wherever a quantity is changing, then derivatives will play a key role. So that brings me to the end of today's lesson. And the next lesson we'll talk about related rates. But before we do that, please review today's lesson and go over the exercise and make sure that you understand them really well, because derivatives are very important sciences and it's important that you understand how they can be used. So I'll stop over here. I hope you have enjoyed the lesson. Thank you.